everybody. Welcome to one of our SASA Spatial Stats Special Interest Group seminars. Today we have Dr. Lisa Kirkland. She literally got her graduated last week, so it's a very, very fresh title, which is really, really cool. So congratulations, Lisa. We really are proud of you.
Thanks.
Yeah, as Lisa said, if you came in when she was talking about it, she's been a student for a long time, but she's really done some really, really great work. And I had the honor of being her supervisor. I wasn't her supervisor from the beginning. I got to sort of come and help out, and I'm really glad I got to do that. So very little of this is my contribution, but at least I got to be there to see it finalized. So Lisa's done a lot of work in rhino poaching, which is obviously a very, very important topic in South Africa. And she's going to tell us about that today. Over to you, Lisa.
Thanks a lot. Okay, so I'm just going to talk about the work I did in my thesis, and yeah, I'm just going to summarize basically the big picture, not too much detail. All right. So the motivation for this work is the rhino poaching crisis. Okay, so there's a lot going on here. I've just sort of started with a global picture with a table there, where you can see that the Asian rhinos are not doing too great. All of them are categorized as threatened. And for the Javan and Sumatran, there's less than 100. So I don't, very little hope there. But the majority of rhinos are in Africa. So there, the white rhino is still near threatened. It's not yet classified by the IUCN as threatened, but the numbers are decreasing really quickly. If you look at the picture at the bottom left, that's the situation in Africa. The top two are for the white rhinos. So the left is the northern white rhino, and they are pretty much extinct in the wild. There are only two females left, and they are non-breeding females as well. They're busy with an operation to put surrogate northern white embryos into surrogate southern white mothers, but they haven't had much progress with that yet. And then the bottom four are the black rhino subspecies. And there you can see in the northern regions, they're really not doing well. And one of them, the western black, was declared extinct in 2011. So in South Africa, we are stronghold to the southern white and the southwestern black. Now, the southern white is quite an interesting story because they were down to like 50 in the early 19th century. So massive, massive conservation efforts in South Africa to get these numbers up, and they were up to about 12,000 or 20,000 in 2010. You know, they started relocating them to their extant ranges. So all of the rhinos in the world right now come from South Africa, from the Umfolozi Park in KZN. So then on the right, we've got the South African situation at the top, and at the bottom in the Kruger Park. So you can see that the Kruger bore the brunt of the crisis. Like we've got a drop there from about 12,000 rhinos in 2010 down to about 2,000 in 2022. And I managed to get some figures for 2023, and it seems to also be going down in the Kruger. I think the crisis is over in the Kruger. They have got it sorted out. Their anti-poaching strategies are excellent. And the poachers, and because there's so few rhinos left, the poachers are having a harder time actually finding rhinos to poach. Now, the orange bars that I didn't have for South Africa, that's all poaching activities, not just arrests. There's a massive amount of activity in the park, and the poaching rate didn't go down really until 2022. You see a slight dip 2020 because of COVID, but only really in 2022 is it going below 8%. And most of those are white rhinos. There were only, I think, 2,000 black rhinos in the park to start with, and there are now about 200. So the poaching poaching rhino specifically has been displaced to other continents, specifically KZN, and also to private parks. So it's going to be important for any private parks or any state-owned parks in other provinces to conserve these rhinos, because it'll be a big shame if we lose these animals after the conservation effort we put in the past. Okay, sorry, I spoke a bit lots over there. Here's just the other kinds of the other wildlife animals inland in South Africa that are categorized as threatened. Yeah, so the work I've done here can really be used for any of these species. We've just kind of tried to use preferences specific for rhinos for this work. All right, so what we really want to do is build a game theory model so that we can help the rangers decide where to send their teams on patrol. It's really just about patrolling. It's not about catching the catching the poachers once they have been detected. Specifically in the Kruger, I know because I read the book that came out 2022. They have response teams that they send out once the poachers have been detected by the patrol team. So the patrol team is really just there to spot the poachers and alert the response team, and just to deter them, because if the poachers see where they are, they won't go there. So we have two theories here that we can align our game with. The first is routine activity theory from criminology, which states that for wildlife security now, that if the poacher and wildlife animals are in the same space in the wildlife park, then there's opportunity for poaching, especially when the rangers are not away. When the rangers or anything in that blue outer triangle deters the poachers, then that's less likely that a poaching event will occur. And then on the right of that figure, on the bottom of that figure, this explains the triple foraging process. And if we look at that, you can see that rangers have the lowest risk when they are patrolling with the poachers alone. If the rhinos are there, there's a chance that the rhinos might get poached. But if the rangers and poachers are in the same cell or patch or whatever you want to call it, then the rangers arrest the poachers. And for the poachers, they want to forage alone with the rhinos, because then there's no chance of being arrested and a high chance of a poaching event. The game also will need to take geographical preferences of the players into account. All right, so here we've got a simple example where we've split an imaginary park into two cells, cell A and cell B. Now, we're assuming that the rangers work as one group, also that there's a poacher team that works as one group, so they can't split up or anything like that. They work as a team, as one player. Here we've placed a number of rhinos in each cell, and we've marked one cell as being next to the border. So this is sort of to demonstrate how we can add that to the utility, because that's a geographical preference, how we can add that to the utility function. So the outcomes, these are the only four scenarios that can occur with two cells and two players. And the outcomes are shown in the right, or in the middle rather. The numbers on the right are payoffs. And this is just a utility function, is a way to quantify the player's preferences for outcomes. So you'll see where these numbers come from in a moment. All right, so now I don't know how familiar you are with game theory, so I'm just going to give some brief background about what's going on here. So in the first column, or we are looking at different payoff structures. So how do I go back? Okay, there. Over here, we can see there's green rhinos that are saved and orange rhinos that are poached. And so we assign 2 to a rhino and we assign 1 to an arrest. Sorry, it's the other way around. 1 for rhinos and 2 for arrest. And then, so these are the numbers that come up, all right? So the first column is the Nash equilibrium. This is when the rangers and the poachers choose where they're going to go independently of one another. In the middle column is when the rangers go first, and then the poachers see where the rangers go, and then they go. And in the last column, the rangers go first. So these things in brackets, this NE means Nash equilibrium. That is the solution concept that we use to solve simultaneous games. The SP and E in the other 2 columns is the subgame perfect Nash equilibrium. And that we use for extensive form games where you have these game trees. So the way you solve the subperfect Nash equilibrium is by backward induction. You first solve in the middle column here where the rangers lead, you're first solving for the poacher at each of his information states, and then you're solving for the ranger. So it's a backward induction process. The Nash equilibrium is a little bit different. You can do it in 3 ways, actually. So the first way is to look at every outcome and see that if your opponent keeps playing that action, could you do better by playing a different action? If you can, then that outcome is not a Nash equilibrium. The way I like to do it is to look at the best responses. So in the top left table there, the rangers are the row players and the poachers are the column players. So if the poachers go to cell A, then the rangers would prefer to go to cell A because they get 5 instead of -2. So that is their best response to the poachers playing A. And then the same for B. And then if you look at the rows, you can do the same for the poachers. Now, if there's an outcome where the poacher's utility and the ranger's utility is circled, then that is a Nash equilibrium. So in the first example, there is no Nash equilibrium, or at least not a pure strategy Nash equilibrium. A pure strategy means that they are choosing one action. A mixed strategy is when they randomize over their actions. Okay, so let's first look at the top row. This is the payoff structure that we want. You can see that the rangers want to go to the cell where the poachers are so that they can capture them. If the poachers are in A, the rangers would rather go in A. And if the poachers are in B, the rangers would rather go to B. So they want to coordinate with the poachers. But for the poachers, they don't want to coordinate. If the ranger is in cell B, they want to be in any other cell but cell B. Okay, so in the same simultaneous game, as I said, there's no pure strategy Nash. But when the rangers lead, they do worse than when they follow. They get a utility of 2, with both the ranger going to A and the poacher going to B. But when they follow, both players go to B, the rangers make an arrest, and their utility is higher. They get 3. Now, the bottom 2 cells are just counter examples for different types of utility functions. So here in the middle, example 2, the rangers prefer to go to cells with more rhinos. So in this game, there's a cell A for the rangers is a dominated strategy. So regardless of what the poachers are going to do, the rangers are always going to go to cell A. So iteratively removing dominating strategies is the third way to find the Nash equilibrium. Okay, and then the bottom is an example where the poachers prefer to stay near to the border. And then in this case, or in both these 2 cases, when there's a pure strategy Nash, then they have the same outcome when playing a sequential game. Okay, I'm going to move on from here. I hope everyone understood that. Okay, so the current state of the art is in the field is the Stackelberg security. Now, where does the Stackelberg come from? Like, why? Why do they want to call it that? So this basically is the Stackelberg duopoly problem from economics. Interestingly, this was done a very long time before John Nash came up with the Nash equilibrium. So in the top picture is the Cournot equilibrium. This is what's happening when they go simultaneously without knowing what the other player is doing. And then at the bottom is the Stackelberg game. So this is a differential game because the total profit is the utility function for each player. And it's a function of both Q1 and Q2, which are the quantities that they need to choose to produce. So when you're doing the Cournot equilibrium, you go ahead and you solve, you want to differentiate that utility function and set the derivative to 0 to find the maximum. And then you're going to solve for Q1 and Q2 simultaneously. But in the Stackelberg game, you're going to follow that same backward induction process that we did before. So you're going to first find the best response for the follower and then put that into the best response for the leader. So essentially, the Stackelberg game is a bi-level game. But in this case, the players are sharing the market. So when we go to security games, does this make sense for the players to share the market? No. One of their assumptions actually are that the rewards are greater than the penalties, which puts you into that payoff structure that we had first, the desirable one. So this is an example of the Stackelberg security game for airport. So let's assume we've got a small airport with 3 terminals. And so the airport security is going to every day patrol or cover a different terminal, but they're going to do this according to some probability distribution. And then the terrorists are going to observe them for a period of time until they gain full knowledge of this probability distribution. They are then going to attack with a pure strategy by choosing one of the terminals. Now, my major problem with this game, or the solution concept, which they call the strong Stackelberg equilibrium, is that they assume that the terrorists will break ties in favor of the leader, or the follower will break ties in favor of the leader. Now, that doesn't make sense to me, because in the security game, it's a totally conflictual game, except that it's not zero sum necessarily, but it is conflictual. So it does not make sense that this breaking ties thing. So let's look at a little example on the right. So this top table is their compact representation, which they like. It's easy enough to put this into the normal form that we are useful, and that is the middle table. So the Nash equilibrium and the strong Stackelberg equilibrium is a mixed strategy where the defenders are going to go to terminal 1 with 0.2 probability, terminal 2 with 0.2 probability, and terminal 3 with 0.6 probability. So let's imagine that the attackers play this, or the defenders play this Nash equilibrium, and let's solve the followers problem. So this beta here in the bottom column are different strategies that the poachers can take when the defenders play this Nash equilibrium. So why the attacker's utility is 0.8 for any strategy you play. So there are multiple optimal strategies for them. Why would they play the one that gives the highest utility to the defender? So they're saying that after the attackers have learned the complete mixed strategy, so they know that the security patrols are going to go to T3 with the highest probability. So why would they attack that one? It doesn't make sense. So how do we, okay, how do we do this in the wildlife security domain? So this is that same example, this one here with these numbers. So the desirable payoff structure. Okay, so let's assume that the poachers play as the leader, and they get, so that this beta in the table on the left is for the poachers. And then let's try different mixed strategies for the rangers and see what the utilities look like. So at first, when I was trying to solve this problem, I thought we need to actually maximize our utility while we minimize the poacher's utility. But that necessarily is not always a good strategy, because if you look at this bottom right graph, you can see that they can actually cross over, right? So you just want to, there may be multiple mixed strategies when you play as the follower, and there may not be a mixed strategy. There might only be a pure strategy, optimal solution. And in that case, I suggest using a near optimal solution so that the ranger's utility is still higher than they would get in the baseline games, the maximum and the Nash, and higher than what the poachers get. And this is possible. So this is sort of the strategy I'm sticking with. So what we're going to do is, like, instead of playing randomly so that all our cells have equal probability, we're actually choosing a subset of those cells that have equal probability, and usually a much smaller subset, okay? Because in real life, you don't just have two cells, okay? So this is a small section of the Kruger Park, and I think we had about 600 cells in this simulation. So these are the problems that we're facing when we compare the terrorist situation to what's going on in the wildlife park. So, I mean, obviously it doesn't scale because there are so many cells. Like, to solve the bi-level problem for the leader, you'd need to do one LP solve for every poacher strategy. So in this case, 600 and something LP solves, whereas the follower's problem is one LP solve. So I think, yeah, let's go there. Okay, so here are the utility functions that are used, and what we want the parameter for arrests to be the highest. So that is this delta parameter for the rangers and the poachers. Because that is what we're trying to do. We're trying to go to where the poachers are and arrest them. It's kind of like, if you can think of the Ching Chong Cha game, you know, you want to randomize. You don't, if you play rock the whole time, you know, your opponent's going to pick up on that. So we need to play a mixed strategy game. So yeah, is the formulation of the leader problem. This is the multiple LPs formulation. There are others. I think the algorithm I used was called the Dobbs algorithm, where they've actually complicated the problem a bit further to assume that there are different poacher types. Then they can linearize it, and it's a lot of math, and very computationally expensive. I don't know why they would further complicate the problem. So my idea was to simplify everything. So if you look at the followers problem, we don't even need to know the utility function for the poachers. The only thing we need to know, and it encapsulates everything we need to know is to learn their mixed strategy. Okay, so yeah, sort of like a schematic of how you would go about doing this whole thing. It looks rough, but it's really basic actually. It's just a lot of like what ifs, like what if we don't have data? What if this? What if that? But it's a simple process really, the first blue lines in the graph are gathering information or any data from any data sources. The second box is more like a modeling process. And then the bottom left section is where we're going to solve for the game. And then the bottom right, we're going to go and we're evaluate it and validate our game. So on the left, I've just got some of the, you can see we make very few assumptions to this game. And there's a whole list of advantages compared to only 2 disadvantages. And look, I'm not a computer scientist, but I'm pretty sure that those algorithms to find a near optimal strategy can be improved on a lot. Okay, so because our utility is only looking at a snapshot of the wildlife density, there's still a lot of variation in how the strategies are executed, and also because the poachers and the rangers are constantly moving. So when I say that the rangers go first in the follower game, it's more about what information they have than about the timing of the game. Look, none of them are stopping for some time to conduct surveillance. There are always multiple poachers in the park, always moving. Same with the rangers. So this is not as simple a problem as the airport security game. Then we designed 2 baseline games, a null game, which is completely random. An example of this is the top right graph, where they're just moving randomly. Whereas in the bottom graph, you can see that the poacher follows a path closer to the river. So for that game, I've designed a game with intelligent poacher movements. So their movements are taking their geographical preferences into account instead of just moving randomly into the next cell. And the geographical features which we've included in the framework are shown in the left for the Kruger Park. All right, so this is how the intelligent poacher movement was modeled. So when you do the null game with random movement, the players don't learn from any events. They just carry on moving randomly all the time. So for the intelligent poacher movements, we've now taken those geographical features into account, like I said on the previous slide. And the poachers are also learning from events. So from the literature, we know that when poachers find some rhinos, that when they re-enter the park at a later time, that they will go to that same place to deplete the rhino resources there before moving on to another location. So when a poaching event occurs, the poachers change their destination cell to the cell where the poaching event occurred. And then they also change their cell when they're arrested. So if they're heading out after a poach and the rangers arrest them, then they change their start cell because it's probably unsafe to use that same place for re-entering the park. Okay, now the spatial point pattern analysis. We could really use a model in that first stage of the game to learn the mixed strategies of the poachers. But we use point pattern analysis because there's no big assumptions on the data. So because we're focusing, so our response, these points, is specifically detected poaching activities. And that process is naturally an inhomogeneous Poisson process because the number of activities is very, very large and the probability of detecting them is very small. So that's great. We only need to while we model the intensity, we need to assume no interdependence between the points. So we first need to account for the spatial variability before we can go and model the interdependence. But there are models that can handle both. So in the top picture on the left is the generated point pattern using those poacher probabilities from the intelligent poacher game. And then on the right is the density and non-parametric density estimate of the intensity. Now this I did see in the literature used for poaching, this non-parametric estimate, but we go ahead and fit parametric models. And this, it hasn't been applied to the poaching problem, perhaps just to population problems. So it's basically a generalized linear model with a log link. And our response is the intensity in the area. And this is a spatially varying intensity because of the inhomogeneous Poisson process. And the Zi are spatial covariates. So the covariates we've chosen is just to calculate the distance from each feature to each cell. And then the model is solved by maximum likelihood. So in the bottom, you see the fitted intensity of the model. And then on the right, the standard error of this fitted intensity. See, it doesn't do so well in estimating that blue spot at the bottom of the region. All right, and then I'm just going to present one of the simulation studies that we performed. I really did a lot there. I can't go through them all right now. But this is a small scale experiment so that we can compare the mixed strategy games as well, because the Stackelberg security game does not scale to that bigger grid of cells. Okay, so at the top is the small section we're looking at, and Rhino density estimates next to that. And then on the right at the top, we've got the geographic utility that's calculated for the rangers in blue and the poachers in red. So if you look at those two, the pure strategy game is depicted there. So where you see an L, that is when the player acts as the leader. And when you see an F, that's when they act as the follower. So interestingly, when the rangers follow, they have the same optimal cell as the poachers. And that is why the game performs so well. Okay, so at the bottom, we've got some solution concepts other than the pure strategies. So the top left one is for the Nash equilibrium. Yeah, you see only about 3 cells or 4, one with very low probability in the rangers mixed strategy, and the poachers have a few more. But yeah, they don't really coincide. Maybe a little. Okay, and then at the bottom is the maxi-min strategy. So this is like the maximum reward in the worst case scenario. Now, so this is the situation when the maximum min is found independently for each player. So they're not like corresponding strategies. It's just that when you play the maxi-min strategy, you're guaranteed to get at least that payoff. And then on the right, we've got the two Stackelberg security games. So the first one is that strong Stackelberg equilibrium, where we've only got a mixed strategy for the rangers, and the poachers choose to go to the cell marked with a P. And then at the bottom, you see the mixed strategy, the near optimal mixed strategy chosen by the followers game. The cell marked with the O is the optimal pure strategy. Okay, so these are the game solutions, and then on the next slide, we can look at the results of the simulation. So on the left, we're showing the expected utility and how it matches with the the simulation because we're drawing from that distribution in each run of the game. So if you look at just utility, the rangers seem to always do better when playing as the follower. They get like 61% of the time they win. And this optimal Stackelberg follower is when the rangers play a pure strategy. But we don't want that because we don't want to be too predictable to the poachers. I specifically chose this utility for this set of strategies, or let me say the number of mixed strategy or the number of pure strategies in the result. I specifically chose a game where the ranger utility was slightly lower than the poacher utility when they play the strong Stackelberg equilibrium, because I wanted to see if utility or better utility equates to more arrests or less poaching events. But when you run, the situation looks better for the poachers when you look at utility, but when you run the simulations over the park or in that section of the park, it doesn't look as good for the mixed strategy follower game. The pure strategy model looks much better, but you don't know actually where the ranges are going to go. So on the right here, if you look at that table, it's better to look at the comparisons when the poachers play and use intelligent movement, because then none of the improvement or to the evaluation measures are because of the poachers movement, because it's held constant. So we know then that the improvements that we see are definitely due to the rangers strategy. The cells that are shaded the same color are where there's no statistical difference no significant difference between the two values. So we do see higher arrests when we use the follower mixed strategy game. What I did notice is that the poaching frequency for the strong Stackelberg equilibrium, game 6, does appear to be lower than that for the follower game. So, I mean, not that much when you look at the intelligent poacher movements. But the reasoning here is that with the arrest factors being so high, the more poacher arrests we make, the less poachers there are to poach, and the poaching frequency should go down. Okay, and I think that's it. Thanks for listening. Any questions?
Thank you, Lisa. That was wonderful. We've got some hand clapping there in the audience. Anyone want to ask something from Lisa? She knows a lot about rhinos, so you can ask her other stuff as well.
No questions?
Doesn't look like it. I think you explained it really, really well. It was a very lovely presentation.
Oh, I hope so.
Yeah.
Thank you.
It was great. Really, no questions, comments? Nobody? All right. Lisa, thank you so much. It was really a wonderful presentation. I see Lindy says in the chat there as well. It was great. You did a lot of hard work, and when you put it in a presentation like that, it looks like it was just, a little bit of work and made some pictures. But Lisa's PhD is like a
300.
brick of information. She really did a lot of work. If anyone is interested in more information, if you want to get access to your articles and stuff like that, just give either of us a shout. Happy to discuss that. But really important work she's done towards rhino conservation in South Africa. And I like also, Lisa, what you said in the beginning about it being applicable obviously to other animals and that sort of thing. I think South Africa is a very conservation heavy country, and it's really important the work you did.
Specifically inland, because obviously, if we go into the water, there's a different situation.
A whole different extraction, exactly, a different covariates and all that sort of thing. It's very much more complicated.
Okay.
Right, thank you. It was really an honor to have you speak for SASA today.
Thanks.
And I do not think you will leave the learning sphere, and hopefully we can have you for a presentation again one day.
Okay. Thanks a lot. Bye.
Pleasure. Have a lovely day, everybody. Bye bye.